Hi everybody. We're going to hop back into part 2 of our breakdown of basic matrix transformations. Sorry. Uh, Not going to lie, I accidentally hit stop recording instead of pause recording when I was recording part 1. So we're going to continue on to part 2 right now. Alright, so we're going to hop back into where we left off in part 1. So we started to look at our horizontal shear. So we had just found that the determinant of the transformation matrix was -1. So if we ignore the sign here, the sign basically just says we've changed orientations. However, if we just look at the absolute value of the determinant, it's 1. Now, what does this mean? If we remember that the determinant of our identity matrix was also 1, and the identity matrix kept it the exact same. And then we remember that when we take our determinant of our transformation matrix, that means that it's like finding the factor that we multiply the area of the rectangle of the first, the factor of the area of the rectangle in the first, what we multiply that by to get the area of the second. So in our identity matrix, we multiplied by 1 because it was the same. Now notice we also have a absolute value for a determinant of 1 with our horizontal shear. This means that the area of this square and this parallelogram is the same, even though I've not drawn it to scale. Let me fix that. All right, so it's not perfect, but they should be at the same height now. Why this makes sense is if you think about the area of a parallelogram, because this obviously looks like a parallelogram now, our area of a parallelogram is the width of our base times the height or the altitude of between the bottom and the top. And we notice that that number is the same. It's still 3 because let's say we take our y value or y coordinate on one of our top numbers in the original, we subtract 0, it gives us a height of 3 on our rectangle. In this case it was a square. Now it still has a height of 3 and a width of 3 for the base. That's still the same. So now we can deduce that it's pretty reasonable for the area to still be the same. And that's like within the realm of reason, as some would say. So, and we remember that the area is equal to the base times height. So not the slant height. So even though this changed, we're still using the altitude of each individual shape. All right, so hopefully you're following along from the first part of the video, as that was a very important part of what we're doing. So I would not recommend starting from this one. So in this one, we're going to keep moving on to our vertical shear, as I hinted on the cover page. I hinted at, rather. All right, so assuming you've been through the first video already, we're going to keep a pretty relatively fast pace so we can get to everything. So to find our output, x prime, y prime, like we have been doing, so if we do a recap of part 1, multiplying, actually put the page I was copying off of away. That's not a good idea. So to recap, if we change this number, it was a horizontal stretch, and then if we change this one, it was a vertical stretch. We just examined for the top right, I believe, which gave us a horizontal shear. The only one that's left is the bottom left, which will give us a vertical shear, as we will look at right now. So what this entails, we are going to transform this with the identity matrix. However, we are going to make that not 0. So let's see what happens there. So we're going to transform our input x and y to give us our output x prime, y prime. So x prime, y prime will be equal to their first times first plus second times second. And then in our second row, our first times first times r plus r second times second. So our output will be x as our x coordinate, and then x plus y as our second coordinate. So what we're going to do is we're going to consider another square. So let's do a 2 by 2 square this time. So let's go with a square. So, oops. So, all right. So I've written this out as an example question out on the screen. You're welcome to pause the video to work through this on your own. Try to wrestle with it yourself, and then I will take it up here. So I can walk us through our first one. So I would say to pause the video now. All right, and we're back. So let's look at our point 2, 2 first, and this will be x prime, y prime. Actually, whatever. I don't really need to write that. Hang on a second. So didn't really need to write that, but we're going to get rid of that. So we're going to transform using this matrix. So we have 1, 0, 1, 1 times 2, 2. That will give us first times first is 2, second times second is 0. In our second row, first times first is 2, and we're going to add second times second, which is also 2. That looks about right. Okay. Yeah. So what this gives us is an output of 2 and 4, when given an input of 2, 2. So if you tried to do it yourself and you got stuck, and now that we've seen the first example, you can pause again and see if you can try to attempt the other ones and see if we meet up in the end. So if you've done all of them and you're just looking for the solution, let's keep going. So okay, let's keep going. So if I transform this oops, let's do 0, 0 next. That's the order I wrote it in. Multiplied by that matrix will give us 0, 0, obviously, as each row is multiplied by 0, 0, so that will result in 0, 0. We go first times first, we get 0, plus second times second is also 0 in each row. So we're not going to go through that. So if we keep on going with our 0, 2, we have 1, 0, 1, 1 with 0, 2. If we take the product and we multiply them, we'll have the first times first is 0, second times second is also 0 for our first row, and then first times first is 0 plus second times second, which is 2. That gives us 0, 2, because so this one was the origin, and then this one was the origin. This one was 0 in the x direction, 2 in the y direction. Let's look at the original point that was 2 over on the x-axis, but no vertical movement. So we have 1, 0, 1, 1 times 2, 0. Oops. All right, so what we have, so our first times first is 2, second times second is 0, and then our second row will be 0 plus 0. So we have 2, 0. And what a great time for a math mistake. So I'm going to slow down a tiny bit there. So what we would have, we would take our first number times in the second row times the first number in the second row to give us our first number that we're adding in our second row of our product. And then our second times second will give us 0. This gives us a point at 2, 2. All right, so notice that, let's see, if I had a point that was at at a place where x equals 0. So it was on the y-axis. It did not move. But notice how if a point was not on the y-axis and y was not 0, the change in y would not be 0, obviously. So I messed it up in the end, but as we can see, this point is not on the y-axis. That means it got sheared upwards. And then this point is obviously not on either axis, and then it also got sheared upwards. So let's see how that looks like if we try to put it on our plane. So it should be on the R2 plane, but we're just going to use the Cartesian plane with x and y instead of x1, x2, because 1 and 2 look like transformations, and that's kind of confusing. So we're just going to use x and y. So this will be the x-axis and our y-axis. We started with a square with points at 2, 2, 0. Oops, that's supposed to be comma, not 2. That is not supposed to be 0 either. 2, 0, 0, 0, and 0, 2. And then if we plot our new points, what this gives us, let's copy and paste the axes. All right, so those are axes of our transformation, or like the transform version, which will be found at, if we plot this, if I try to do this properly. So this point and this point stay the same because y was 0, and then adding y equals 0 to this keeps it the same. So we have here, these 2 points are constant or do not change. Then we have a point here and another point here. Hopefully that's accurate enough. So if I trace this, hopefully that makes the shape. That's good enough. So we have a point at 2, 4 and 2, 2, and then those points stayed the same. All right, so that's why it's called a vertical shear. So everything that's not on everything that wasn't on the y-axis where y equals 0 was shifted upwards. So if the whole square wasn't on the on either axis or not on the y-axis, the shears, each type of shear would probably just be a shift. But since these are usually we're given like a square, that's like the easy one to start with. So that's going to look like it's been sheared. So only one side has been moved up, and now it's been distorted, let's say. So let's look at the determinant of this matrix again. So if I look at the determinant, so the determinant of 1, 0, 1, 1 is equal to 1 times 1 minus 0 times 1, whatever. It's still equal to 1. That means that the area is still the same. So the area of the square created here in the original square is the same as the area in the parallelogram. So maybe I should have used something that wasn't all ones to make it even more of a change, but whatever. So obviously, just like before, this can be due to the formula of the area of a parallelogram. So if I take base times height this way, so this was the base, this was the height of our original. This is the base, and then this altitude is our height. So the areas will be the same because that's the same distance, obviously. So hopefully that helps clarify that part. And then for a general form, so vertical shear, find. So when I transform my identity matrix, so 1, 0, 0, 1, but with something else instead of 0, I would get a vertical shear. Now, we've looked at all 4 of them individually. Let's look at some combinations and then see how those might change as well. All right, so what we have on the screen, so remember back in part 1, we looked at horizontal stretches and our vertical stretches. So if I combine these together into one statement here, so stretches so if I have both the h and the v, I didn't want to use x and y because we use x and y to transform them. So let's look at some special cases and some intervals where these do different things. Hopefully that sentence made sense. Like intervals for the values of h and v. So in the original definition I just wrote up on the top of the screen, I put that h and v can't be 0 because, well, they can be 0, but it won't have any effect because in this one, if h was 0, this would be an identity matrix and nothing would happen. So it would be like a horizontal stretch, by a factor of 0, which would do nothing. And that's like redundant, right? And then same here, a vertical stretch by a factor of 0, that's not really a thing. It won't make it 0. It would just make this the identity matrix and then keep it the same thing. It would have 0 effect. So I'm going to write that down. So if h or v, or another way to write this is a set with h or v is equal to 0, not element of 0, is equal to 0, h or v is equal to 0, or a set with h and v in it, something's equal to 0, that would just be identity matrix. So that would do nothing. All right, so we briefly touched on some of this as part of part 1, but we're going to look at some of these as well. So if h is greater than 0, then it would get bigger in the horizontal direction. So it would get, so the x components that aren't on the axis would get greater. Now, if let's go if, oops, that's not right. If h is, let's say, between, so it'll be soft brackets for our interval, between 0 and 1, then if we had our original square, everything would all the x components that aren't 0 will get smaller. So obviously this is just another way to say 0, h is greater than 0 and less than 1. But I just wrote the h in a different spot. So this means the same thing. So, oops, sorry about that. So, and then this like fancy e is an element. So h is part of this interval. So let's touch on that later. So, however, we did not really address if h is less than 0. So let's look at that other case. So if, actually, this is supposed to say if h is greater than 1 because, yeah, that's wrong because we define what less than 1. So if h, so now if h is, I guess, less than -1, so it's like a bigger negative number, so it'll be less than -1. Let's say we started with our square, our positive square, we would get a longer rectangle once more. However, it will be reflected in the y-axis, so be horizontally. A horizontal reflection is a reflection in our y-axis here. So this would give us actually, let's draw the full axis. So this would give us an extended rectangle horizontally, but also reflected horizontally. Now, for this other case, if 0 is greater than h, or h is greater than 0, but also, well, h is less than 0, but greater than -1. Sorry, I can't think negatively right now. But so if we started with our square, we would get a skinny negative square. So, or like a square or a rectangle that has been that has had all the magnitudes of their x components be smaller and reflected in the y-axis. So to generalize this part, if h is positive, it will stay, it won't be reflected, no reflect. And then if h is negative, then the yes reflection in the, I'm running out of room to write that, in the y-axis. So some of us might have trouble remembering that, but like a horizontal reflection is actually a reflection in the y-axis. So that might be a bit hard for some people to envision, but easy for others. So let's look at v. A lot of these apply for v as well. So if v is greater than 1, then your square will turn into a taller square if v, okay, I don't really read it this way, so whatever, let's do it that way then. So if v is greater than 0 but less than 1, then it will get, that's not a great drawing. If we start with our square, it will get squashed down, but still be the same width. So should have left more room for that. Now, if v is greater than 1, or greater than -1, oh, that's not good. So v is less than -1, so bigger negative, sorry. If I started it with this, it would be a taller, rectangle. However, it will be in the negative direction, as it's been reflected vertically, so it's been reflected through the x-axis. So if v is part of the set between 0 and -1, or proper form would be -1, 0, then our square we started with would get reflected in the x-axis, so reflected vertically. However, it will still be squashed down a bit. So let's make the original one bigger. All right. So if v is positive, then there is no reflection in x-axis. Sorry about that, I can't read that either. So let's take away from this and then zoom in. So okay, so hopefully you still remember what v is. In the x, oops, that's wrong again. In the x-axis, and then if v is negative, oops, then there is reflection in the x-axis. So it's like a vertical reflection through the x-axis. So let's see if that fits. That does fit. Okay, so so we can have stretches in either direction, both at once, and if we have a negative of either number, we can have reflections. So our square can end up in any of our 4 quadrants if we combine these together. Now, let's address another case. All right, so what you see on the screen, we're going to see what happens when h equals v. So if the horizontal stretch factor is the same as the vertical stretch factor. So what that would look like, it would be stretched by the same factor in both directions. So it's going to be like if you took a picture, or in case anything, and then it all got scaled by the same factor. So let's go ahead and look at an example. So let's say we have, we're going to go and take our squares again. Let's say we take our square, 2, 2, and then transform by 3, 1, 1, 3. All right, so you should be able to try this on your own. You're welcome to do it right now. And if we look for our output, x prime, y prime, going to be equal to the matrix times our input vector, we would get our first times first is 6, plus our second times second is 2 as our first row. And then our second row, first times first, is 1 times 2 is 2, plus 3 times 2 is 6. So this would give us 8 and 8. So now if we look at the determinant of this matrix, we know that the determinant of 3, 1, 1, 3 would be AD minus BC. So we have 9 minus 1 would be 8. So the area, that means that the area of the rectangle created by the diagonal, if it's diagonal were these matrices, that means that the area grew by 8 times. So if I did take, if we did look at it graphically, let's say this was 2 and 2, and then the area would be 4. And then we had our output, 8 by 8. Well, this is not going to be the scale, but whatever. So let's put our axes on. Shouldn't be that much longer. So be 8 and 8. If we look at our areas, so this area would be 64. And now that doesn't make sense. All right, so maybe that that thing applied to just a few examples we did, but obviously what we know for sure is that the determinant is greater than 1, so obviously it's going to be a lot bigger than the original, even though there might not actually be some relationship between that. So I'm going to have a look at the examples I started with and get back to that on that. So when the determinant of the transformation is 1, then the size of the shape created will be the same size, and if it's greater than 1, it'll be bigger. Smaller than 1, it'll be smaller. All right, so now we're going to address what happens when the determinant is equal to 0 of our transformation matrix. All right, so we're going to see what happens if we transform x and y by this matrix. So To take the determinant equal to 0, we can notice that there are two identical rows, which means that if we do row operations, we'll get only one leading one in a row of zeros. So that's also equivalent to the determinant being 0, and the columns are also linearly dependent, so that is also another indicator that the determinant is equal to 0. So everything is interconnected in a way there, but let's bring it back in and focus on our transformation. So let's say we have our input. So let's look for a generic output here. It's going to be equal to this matrix times x and y. So we, for first times our first, gives us x plus 2y, and then we have x plus 2y. So that doesn't simplify further, sorry. So let's see what happens when we have our two rows in our transformation being dependent on each other. So let's have a look at our square again. So if we take our 2 by 2 square, let's see what happens if we plug that in. All right, so I've written it in question form so that you can apply it, on your own. So what this gives us, you have 1, 2, 1, 2. Oops, we're going to multiply it by 2, 2. So our first times first is 2. Second times second is 4. First times first of our second row is 2, and then we have 4. So we have 6 and 6. For our other points, we can work through on our own, and then we'll meet up at the end. All right, so if I were you, I would pause the video, work through it on your own, and then once we come back, my 4 points will be on the screen. All right, we're back. So when doing your multiplication, you should have gotten these 4 points. So let's have a look at what this looks like. So in the original, we had our square. Actually, let's draw the square first. That's easier. We have our square on our axes, and then this has been transformed. So we had a point at 2, 2. Now we have, let's put on our axes. We have a point at 0, 0. We have a point at 2, 2. We have a point at 4, 4, and a point at 6, 6. So what that gives us is a line. So you might ask, how do we go from a square to a line? Now, if we go back to what we know about our determinant, and the determinant is like what we multiply, and how the effect is on the area. If the determinant was 1, then the area would stay the same. It was greater than 1, the area would grow. If the area was less than 1, it would shrink. Now that our determinant is 0, let's say we multiply this area of this square by 0, and then a line has an area of 0. That's one way to look at it. Also, I also briefly mentioned that if I put this matrix into a row echelon form, that would give me, if I took row 2 goes to row 2 minus row 1, we would get a row of zeros. Oh, I should write out the row of zeros. So that row of zeros means that I have eliminated one dimension. So this line only has one dimension now, because even though it's in the 2D plane, or R2, it only has one thing you can measure. You can only measure its length. Like lines are like, obviously lines of thickness when you write them out on paper or on a screen or whatever. But there's only one thing that's important about it. It's like its length, right? Our square has a length and width. This only has a length. So we've basically eliminated one of our dimensions. So this has an area of 0. If I had labeled these points, let's say this is A, B, C, and D, A, B, that looks weird. 0, 2, C, and D. Obviously, that's in a weird order. I would get A prime. I would get B prime doesn't change because it's a 0. C prime would be at 4, 4. And D prime would be at 2, 2. So all the points that we had that originally made a square are now in a straight line. So what we have, since we have one leading one dimension is kept, and the other one is gone. So obviously we went from a 2D shape to a one-dimensional line. So the key point here is that by transformation of a singular matrix, we went from a 2D shape to a one-dimensional line. So if we had number of 0 rows is equal to number of dimensions lost or killed or whatever, eliminated. Okay, so yeah, so obviously there's infinitely many ways to write this, like the number of free variables in this matrix is equal to the number of variables lost, or the number of rows minus the number of leading ones also gives us the number of rows that we are, a number of dimensions we are losing. So we obviously went from a 2D to a 1D. So and as our determinant equals 0, our area of this, the area of a line is obviously 0, because either your width or your height or your length or your width, one of those is 0, so then they multiply and then you get 0. Now if we go back to our 0 transformation for a second, this also had a determinant of 0, so however, it also had 2 rows of zeros. That means it killed 2 dimensions. So if we started with a square in 2 dimensions, everything or anything in 2 dimensions, it all went to a 0 dimension thing. It's just a point, right? A point, the only thing that you can describe a point by is where it is. It doesn't have a size. It's just a point in space. So notice how we have 2 rows of zeros, which means that if we were solving an equation with this, there would be 2 free variables, and then so there's 2 0 rows. That means 2 dimensions were gone. We went from 2D, which would be a shape, and we went all the way down to a 0 dimensional point, because the point doesn't have a size in either direction. And we go back to our singular, we only had 1 0 row, which means we got rid of 1 dimension to go from 2-dimensional to 1-dimensional. So hopefully both parts helped. I didn't think it'd get this long, but hopefully it's thorough enough and that you could watch this on double speed, unless you're following along very closely. And so best of luck with your work, and I hope you have an amazing day.